what is there in this question now. The electrical circuit shown is used to investigate the temperature change in a wire that is wrapped around a mercury in glass thermometer. Okay. A power supply of EMF 24 volt and of negligible internal resistance is connected to a capacitor and to a coil of resistance wire using an arrangement of two switches. So it means like this is a battery, does not have any resistance. This is a capacitor, and this coil is having a resistance R. The switch S1 is closed, and few seconds later it is opened. Then switch S2 is closed. Now, what do you mean by this statement clearly? Like when switch S1 is closed here, so what happens? The charging of the capacitor is taking place. So the charging of the capacitor is taking place. It means that this is becomes positive, negative. There is a charge Q, and Q will be given by the formula Q is equal to CV. Capacitance is given, voltage is given. You can find it Q is equal to CV. Then switch S2 is closed. So what is happening after that? After that, switch S2 is closed and S1 is opened. So S1 is now not working, battery is disconnected now, but now this is closed. So all of the energy starts discharging. So capacitor is discharging now. So the current starts flowing through this circuit, and obviously all of the energy which is stored in the capacitor will be converted into heat, and that heat is being measured by the thermometer. This is what is happening. Let us read the statement further now. So the capacitance of the capacitor is 22 millifarad. Calculate the energy stored in the capacitor when it is fully charged. Okay, so this question is simple, and the energy we know is given by the formula half CV square. We can just sub in the values. Half 22 milli means that you have to divide it by 1000 here, into the potential battery is 24, so it is 24 square. There is no resistance in the series with the capacitor, otherwise the potential difference will be shared between the resistance and the capacitor, but that is not the case. So all of the 24 voltage is across the capacitor only. So this is the energy, and overall it will be 0.022 into 24 square. Well, this is going to be the answer. So I'm not having my calculator now, so we have to just see what is the answer. Okay, so this is how we do it, and half CV square, let us see what they are doing. Yeah, they have done the same thing, half CV square, and this is 22 milli. I think here is the typing error there. See, 22 milli, it has to be converted like 0.022, and then only, but they have not even written the answer there. So whatever is the answer that you would be getting, that answer will be written here. Here in the mark scheme, there is clear-cut typing error, so don't be confused about it, okay? Let us now move to the next question. So the next question is, the resistance of the wire is 8 ohm. Determine the time taken for the capacitor to discharge through the resistance wire. Okay, so now we are talking about the time taken to discharge. Assume that the capacitor is completely discharged when the potential difference across it has fallen to 0.24 V. So I think this formula is given in the data booklet also. So V is equal to V naught e raised to power minus t by tau, where tau is the time constant. The same formula exists in the case of charge also. So there are many other formulas here. They talk about the current also, but I don't want to get into that as of now. So let us only concentrate on the voltage. So the voltage is 0.24. The maximum voltage was 24. E raised to power minus t by tau, where tau value has to be first calculated. It will be equal to RC. Resistance is 8 ohm and the capacitor is 22 millifarad. So this is the value of tau. We are going to substitute this value here, but before that we will take logarithm here. So it is clearly 1 by 100 is equal to e raised to power t by tau. You just take the logarithm. This value will be negative also, but we have to use the calculator for this. And you can substitute the value of tau in this equation, and thereby we will find the time at which so and so situation will be there. So we can say that in this much of the time, the capacitor will be fully discharged. Is it okay? Let us now see in the mark scheme what are they doing. This is I think question number 2. Yeah, let's see. Yeah, even they have done the same thing. You see, 1 by 100, so ln 0.01 is equal to minus t divided by rc. Now they are substituting the value of the capacitance in the correct manner. In the earlier one, question number 1, there was a typing error. Clearly you see it is 0.022. So 0.81 seconds. So the time taken is 0.81 second. It means not even one complete second is taken in getting discharged, and all of the energy is lost. Okay, so this much is the time taken now. Okay, so let us move to the next question now. 1, 2, 3. Yeah. The mass of the resistance wire is taken as 0.61 grams, and its observed temperature rises 28 Kelvin. What is the specific heat capacity of the wire? Include an appropriate unit for your answer. So you have to give the unit also, but that is always important. You must always give the unit, whether it is written or whether it is not. So definitely we will first find the total amount of energy which is lost in the resistor, and that energy will be equated with mc delta t clearly, and c is the unknown, m is given, delta t is also given. Now, how are you going to find the value of Q? So people would be like, it is highly tempting to use this formula I square RT. But the problem is that this resistor is not even connected. It is not connected with a constant voltage battery. So it will not be having a constant value of current in the first place. So you cannot use this formula. This formula is used only when a battery is connected with the resistance. Okay. So we are not able to use this formula. Another thing is that the resistance of the coil is not given in the question. Okay, so no, it can be taken as 8. No, yeah, it is given. It is given. We can take it as 8 anyways. So that is not the reason. Sorry. But anyways, we cannot use the formula I square R. So what are we going to do? We are just going to assume that all of the energy which was stored inside the capacitor is exhausted in the resistor. So what was the energy that we found earlier? And that energy was half CV square. Now that will be mc delta t. From this equation, we are going to find the value of C. So this value of Q, it was not found, and the answer was not given. And I told you that we have to calculate it, and we will see what they have done in the mark scheme. I think they would be doing the same thing. Okay, let us go for the mark scheme now. Yeah, you see, in the question number 3, they have done the same thing. So Q, as they have calculated, they have taken it to be just 6.3 joule divided by the mass, which is 0.61 gram. I remember it was 0.61. You will be dividing it by 1000 to convert it into kgs. And the change in temperature was 28 Kelvin. So you can write it as 28. So the unit has to be found. It will be joule per kg Kelvin. So the unit will be joule per kg Kelvin. Simple. And this is the value that they are trying to calculate. And the answer is 370. So your answer will be 370 joule per kg Kelvin. And 28 Kelvin, like you try to understand, the temperature difference is 28 Kelvin. And what is the time taken for that? Not even 1 second, 0.81 second. And the temperature that was risen, the temperature that rose there was 28. Anyways, okay, so this is question number 3. Let us go to question number 4 now. So just one other energy loss in the experiment and the effect it will have on the value of the heat capacity of the wire. Okay. Uh, so what can be the other losses here? Well, we can say that the heat is produced here, but all of the heat is not absorbed by the mercury. So the temperature rise, which is depicted by the thermometer, which is 28 Kelvin, will definitely be lesser than what it should be actually. So some heat will be lost to the surroundings or the environment. Some heat will be taken by the thermometer itself. So definitely there is more heat that was actually given by the resistor, but the heat which is measured by the thermometer is lesser. So the specific heat that we are now calculating, that is more, because the temperature rise is lesser. So Q is equal to mc delta T. Clearly, you see, the Q is the constant value, but here the temperature rise is not sufficient. So clearly the specific heat value that we have found is more. So it will be lesser than what the value we have found. So this should be the answer. Let us see what is written in the mark scheme. Yeah, some thermal energy will be transferred to the surrounding, some to the thermometer. Specific heat by the student will be larger. Yes, I told you that. So if the temperature range is lesser, like 28 Kelvin is less, technically it should be more than that. So it means that the specific heat value that you are finding is definitely more than what it actually is. Okay, that will be larger than the accepted value. Yeah. So this is how we do this question, my dear student, and I think no part is left for this now. Everything is over. Yeah, so this is how we do this question, and thanks for joining. And please share the video with all of your friends. Do tell them to join the YouTube channel if they really want to access the uh, this paper two questions here on my YouTube channel. Okay, then all the best. Bye.